In this video, I'm going to give an overview of analysis tools in the QED.net software that are suitable for fitting and filtering data. I'm then going to outline which of these tools are generally most appropriate for various applications and use cases. So why would you want to fit or filter a map in the first place? Well, many form and texture tolerances that you might find on an optical drawing require some form of fitting or filtering in order to evaluate those tolerances. Secondly, there are vast quantities of information in a map. Typical aerial measurements include on the order of 1 million data points, and so you can be very helpful to divide this information up in various ways. Here's an example. So here I show a raw map on the left that is the initial measurement of, in this case, an aspheric surface. And so you can imagine dividing this map into different components. Its alignment error contribution, a radius fit, surface form error, and a mid-frequency residual. And so this is an example of using various fitting and filtering tools in order to create this separation. QED.net has around 20 analysis tools that are related to fitting and filtering, at least as of 2026. And so let's start by classifying them by their computational or mathematical characteristics. So here is a current list of analysis tools most relevant to fitting and filtering data. Let's first highlight the ones that perform their calculations globally. Polynomial fitting and Fourier analysis fall in this category. Now let's highlight the other tools which perform their calculations locally. Basically, each output point in a map is calculated from a neighborhood of points around the corresponding point in the input map. The moving average is a good example of this type of tool that you might be already familiar with. These tools can be further subdivided into linear and nonlinear versions. Basically, is the result from the calculation a weighted sum of the neighboring points, in which case it's linear, or is it a more complex function, making it a nonlinear tool? Now let's consider some specific applications in which you might want to use these fitting and filtering tools for. So as alluded to previously, the first is evaluation of surface tolerances. And so on the right here, I show a reduced version of an ISO 10110 compliant print. And so we have irregularity evaluation, which is going to require alignment error removal. We have a radius of curvature specification. We have a Zernike specification, both for an individual term as well as a residual. We have a local slope specification, which will require some detrending. And then on the surface texture, we have a Bandpass RMS, and we could also have a power spectral density specification, though this particular drawing does not have one. And this would be for evaluating waviness or roughness. So another application is general process evaluation and development. Basically, you want to examine a map more closely. And so some things that you might want to do include smoothing a map to remove spikes and outliers, examining mid-high spatial frequencies more closely, or perhaps perform some quantitative assessment of the convergence of a process or the repeatability of metrology. Okay, now let's look and see which of these tools are appropriate for those various applications. So for alignment error removal and radius fitting, the fitting and low-order aberration tools are most appropriate, and the Zernike removal tools can sometimes also be used for this purpose. For Zernike term and residual tolerances, naturally, the tools with Zernike in their name are most appropriate. For detrending, which would be removing the low-order form prior to some further analysis, such as a slope or other mid-frequency, high-frequency analysis, the fitting tools, whether polynomial fitting tools, generally fall in this category. but there's another local tool that can be appropriate for this application as well. For doing bandpass RMS and power spectral density tolerances, the Fourier tools are appropriate for these tasks. And finally, for general process evaluation and development, depending on what you're doing, all of these tools can be appropriate in different specific instances. So, how do we select the right tool? So, as mentioned before, the application is the main driver in tool selection. Each application has typically only a few tools that are most appropriate for that use case, except, of course, for general process development, in which case any of them might be appropriate. But from there, some distinguishing features of the individual tools are what input parameters are needed. Are the individual terms or coefficients from a fit meaningful? And so this is a case of where you might need an orthogonal polynomial fit versus not needing that. Note that orthogonality often depends on the aperture shape. So a fit that is orthogonal over, say, a circular aperture, such as Zernike's, won't be orthogonal over a different shape aperture, such as a rectangle. And finally, how does the tool respond to various characteristics of the map? Edges, especially ripped or rolled edges, the specific aperture shape in question, whether there are spikes and outliers in the data, and how the tools handle invalid data points. And so these are all nuances that will make one tool perhaps more appropriate than another. So in future videos, we'll go in deeper dives on some of these various applications to indicate how you might use the tools to perform these various operations.